Okay, standard electrode potentials. So the standard electrode potential for a cell is going to depend on the specific half reactions that you're looking at. And it's going to be a measure of the potential energy difference between the two electrodes. How strongly do the electrons want to flow from one to the other? So we can think of each electrode in the half cell as having its own potential, a standard electrode potential. Just like we can look at the ends of a river and say, well, this has a certain elevation and this has a certain elevation. Bigger elevation change, more water, the faster the water flows. Bigger potential changes, the faster the electrons are going to flow. So this standard cell potential here is the difference between the electrode potentials. Just like in elevation, it'd be the difference between the beginning and the end. This is the difference in the potentials. So, analogy with water, we got 2 water tanks, 2 water beakers connected by a pipe. The water is going to flow from the one with the higher level, the higher potential energy, to the one with lower potential energy. Right? I think we all have enough experience with water that we can recognize that's what's going to happen. We're not going to have the water flowing this way until that beaker starts overflowing. That's just wrong, right? So water flows from the higher potential energy to the lower potential energy. When we connect 2 half cells, electrons flow from the side with more negative charge, greater potential energy, to the side with more positive energy, lower potential energy. Make sense? So potential energy is electrical potential energy, very similar to physical potential energy. Okay? We cannot measure the potential of an electrode in a half cell directly. So this is kind of like with energy, like with enthalpy. It's like, well, we can't measure just the enthalpy of this one thing. And so what we did is we decided, okay, we're called elements in their standard states. We're going to say those are 0, and we'll measure the change from there. Like with elevation, we chose sea level as 0, and then we can measure the difference. So here, what we're going to do is we're going to assign 0 to a particular half reaction. And that half reaction is this one. Hydrogen ions gaining 2 electrons to form hydrogen gas. And this is referred to as the standard hydrogen electrode, or SHE, standard hydrogen electrode. Why did they choose this? Well, it doesn't really matter, does it? But that's what they chose. So everything's measured against this. It's probably the simplest thing they could come up with that had standard states, right? So you can get a 1 molar H plus solution quite easily. If you were trying to do, iron or something, 1 molar iron ions, pretty concentrated, you might have a hard time because they're just not even going to be soluble. But hydrogen ions, no problem. 1 molar hydrogen ion solution. And then in this tube, we are pumping hydrogen gas. So there's 1 atmosphere of hydrogen gas in here. And we have the platinum electrode. So that is defined as 0. And everything else is measured relative to that. Any questions? So we could hook up a zinc half cell here to a standard hydrogen electrode. So over here with the zinc's losing 2 electrons, so this is the anode, and this is going to be the cathode. And the electrons are going to flow from the anode to the cathode, and then the charge will continue to flow as the ions move in the salt bridge. Over here, we've got 2 hydrogen ions receiving 2 electrons to make a hydrogen molecule. if we put a voltmeter up here instead of a light bulb, we can measure the difference in the potential between those two electrodes. And so the difference is 0.76. So that is the potential of this half reaction. This is relative to this one that we said is 0. So E for the cell, each of these is a half cell, like they have half reactions. For the overall cell, it's the difference in voltage between the cathode and the anode. The cathode's the final state, the anode's the initial state. So we always draw it this way with the anode on the left and the cathode on the right. And that's where our new phrase, an ox and a red cat, comes in handy. Because reading left to right, an ox, red cat. This is the anode, that's the cathode. So this is initial, that's final. The cell potential is going to be the potential at the cathode minus the potential of the anode. So this is the 0.76 is that difference. So if this is 0, and we've got 0.76 volts is equal to, what's the potential for this one? This is the difference, 0.76. It's the final minus the initial. 0 minus E, what's E? Negative 0.76. So over here, this is negative 0.76 volts. Any questions? So the measured potential of the cell is positive 0.76. As often happens, I jumped ahead. So the electrode potential for that zinc 2 plus half cell, we figured out this way. So the cell potential is 0.76. That's the cathode minus the anode, the final minus the initial, 0 minus the anode, so then the anode must be negative 0.76. And we can think of it this way. A more negative electrode potential means that the electrons are want to leave, right? Because we've got negative charge repels electrons. So this has a negative potential. The electrons are like, ooh, that's negative. I don't like that. I want to go to the other side. And so then that's what happens. Any questions? If we measure a copper electrode, copper 2 plus, there's not a picture, no. We measure this relative to the standard hydrogen electrode. The cell potential will be negative 0.34. So here's the cathode is the hydrogen electrode, and that's 0. And our negative cell potential here, negative 0.34, volts equals 0 volts minus the potential of the anode. So then the potential of the anode is plus 0.3 volts. If the anode is plus 0.3 volts, are the electrons going to want to leave? No. They're like, oh, this is great. We're attracted to this. We're going to stick here. The negative cell potential says that this is not a spontaneous reaction. Electrodes are not going to flow from the anode to the cathode. This is non-spontaneous. The more positive the electrode potential, the lower the potential energy of an electron at that electrode. So this is positive. So the potential energy for the electron is lower here. So here we're showing that lower. And so the electrons want to go from here to here. They do not want to go in the opposite direction. Any questions? We'll learn later that we can make them go in that direction, but instead of a measured potential that we could use, electrons flowing spontaneously, what we have to do is we have to force electrons into it, and then we can make it go in that non-spontaneous direction, but it won't give us electric current. It's going to use electric current. So the copper electrode's positive relative to the standard hydrogen electrode, meaning it's drawing electrons away from it. The zinc electrode was negative relative to She, so it tends to repel electrons towards the standard hydrogen electrode. So if we combine these two together, we're going to have electrons moving from the zinc electrode to the copper electrode. So by convention, standard electrode potentials are always written for the reduction half reactions. These are the reduction half reactions. So that's where you have, this is in the anode, and your standard hydrogen electrode is the cathode. So when we did that, we found out that the potential for this one was positive, and the potential for that one is negative. Wrong book. So, to calculate the standard cell potential, it's the cathode minus the anode. And you look up the reduction potentials in a table such as this one. These are all for the reduction. So these are all gaining electrons, and then this is the potential relative to a standard hydrogen electrode. I personally find that to be rather confusing, because you have to figure out, well, which one's the anode, which one's the cathode, and wait a minute, which one was subtracted from which? It's easy to get it backwards. So this is what makes a lot more sense to you. This is the method I'll be using in class. You can also add the half reactions and add the cell potentials. So you're going to look at, well, what's actually going on here? So here I have, this is written as a reduction. This is also written as a reduction. If we're going to change the direction of if we're going to flip the direction of the reaction, we're just going to change the sign of the potential. So this was an ox and a red cat. This was oxidation. Oxidation is loss of electrons. So this is written as reduction. So what's really happening there is the reverse reaction. So this is reduction, this is reduction, this is oxidation. So when I change the direction, I change the sign. So the way I think about it is, okay, this is what's happening on one side. That's what's happening on the other side. I'm going to just ignore that. I used that to find this. Now I'm going to add these together. that's going to be, 0 volts plus 0.76 volts, which equals plus 0.76 volts. This method, let's maybe do this in a different color. This method, we're going to say, okay, this is at the cathode, and this is at the anode. So we're going to take the cathode minus the anode. So our cell potential is going to equal the cathode, which is 0, minus the anode, which is negative 0.76. Yes?
Why do we have to make them both reductions at the beginning to then just switch it back to oxidation?
That's a great question. Why do we have them both reductions and then we're just going to switch the one? The reason is because of the table. They are all written as reductions. They don't have a corresponding table with oxidations because it would kind of be redundant. It's easy enough to figure out what the oxidation is. Switch the reaction, switch the sign. Okay, so that's why we would start with this information, right? This is the standard way that people do it. There's nothing wrong with it, except that I personally find it confusing because I don't like thinking about what's the cathode and what's the anode and which one is final and which one is initial, and I get confused. And I think students do as well. What I like about this is I don't have to think about what's the cathode or what's the anode. I just need to know what direction is this one going, what direction is this one going. Oh, that one's going in the opposite direction, so I'm going to write it backwards, change the sign. And then if I want to know the cell potential for those two together, I add these together, and I add those together, and I get my answer. And this is a lot like adding delta G's or adding delta H's or something, right? Any other questions? So this is a table from your textbook. And again, when you're doing mastering chemistry questions and you need to look up a value like an equilibrium constant or a cell potential or something, look it up in your textbook, because if you look it up online, there are going to be slightly different values because these are not exactly correct. And these are the conditions under which the book is asking you questions about. When you find something online, it might be at a different temperature, different concentration or something. So you could do the problem correctly with slightly different constants and end up with the wrong answer, and that's like super frustrating, right? So all of this information is in the textbook that is attached to Mastering Chemistry, and you can just go into the appendix and look at it. Yeah? Or just stretching? That's okay. So these are all reduction half reactions. And they're written, there's the top of the table. They go from a low tendency towards oxidation to a high tendency towards oxidation. And the standard hydrogen electrode is in the middle. That's where the potential for the electrode is 0. So you need to know what that zinc electrode, what its potential is. You find it right here. The reduction would be negative 0.76. So the oxidation is plus 0.76. So the potential of She, standard hydrogen electrode, is exactly 0 because that's what we defined and we measured everything from. Things that have a greater tendency toward reduction are going to have positive potentials relative to that. things with lesser tendency towards reduction are going to be negative. The cell potential is the difference between the cathode and the anode. Standard cell potential is positive for spontaneous reactions, negative for non-spontaneous reactions. So here, the sign convention with E is like entropy, right? Entropy, a spontaneous change would be an increase in entropy, right? Spontaneous thing happening here is a positive cell potential. Okay, it's a common kind of question. Use the tabulated standard electrode potentials to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees Celsius, which is the standard temperature. The equation is balanced, so we don't need to mess around with that. So what we need to do here is we need to identify what are the two half reactions. So I've got iron and I've got chromium. So the lead. The leads are together in one half reaction, the chromiums are together in the other. So 3 iron going to 3 lead. Yes, thank you. I was checking. 3 lead ions going to 3 lead atoms. And there's going to be electrons involved. Where are the electrons? They're going to be on the more positive side. So, because this has to be electrically balanced for charge. So I have 3 positive 2 charges. That's a total of plus 6. So that's going to be 6 electrons over there. The other half reaction is the chromium. For this one, the product side is more positive. 2 plus 3 charges, so we also need 6 electrons over here. If you pull apart a balanced redox reaction, the electrons are always going to be the same. So the normal method is you need to identify which is at the cathode, which is at the anode. Take the cathode potential, subtract the anode potential. Yuck. This is what I do. Okay, PB2 plus and PB. I think we have to go back to the table. Just double check. Yeah. So we're going to go look that up. And here we have PB2 plus and PB, right? It's only one of them instead of 3. That's why the electrons are 2 instead of 6. But it's the same 2 species, lead 2 and lead. And the number here is negative 0.13. This is written as a reduction. You've got the electrons on the left side. What do we have here? This is written the same way, right? The electrons are on the left side. We've got lead 2 plus electrons making PB. Yes?
Could you not just see that the starts from the solid and goes to aqueous since all the reductions are aqueous to solids? So then you can tell that one's the oxidation.
Yes, that's a great observation. Couldn't you just see that this one's going from a solid to aqueous and say, well, that one's going to be the oxidation? It is, but you're not always going to have a solid. Yeah. Sometimes you do, sometimes you don't. But that's a great observation. So what was the number again? Negative 0.13. So 2 plus on the left, 0 on the right. 2 plus on the left, 0 on the right. Same direction, right? So the electrode potential is negative 0.13 volts. It's in the same direction. I'm just going to write it down as it is. We are not going to worry about the fact that it's multiplied by 3. We don't multiply the potentials by 3. The other one is chromium and chromium-3. So we're going to go look for that one. Here's chromium-3. There's 2 of them. So this one's going to chromium-2, and this one's going to chromium-0. This is the one we want. So we've got chromium-3, and we've got chromium. And this is negative 0.73, but this is backwards of what we have. So we're going to change the sign because we're writing it backwards. So we take this guy, negative 0.73, and we're going to write positive 0.73. And then we're going to add those together. So what I did is I pulled this apart into the half reactions. I looked the half reactions up in the table. One is always going to be backwards. One's always going to be forwards. I find the numbers associated with those reactions. The one that matches, you just copy the number. The one that's backwards, you change the sign. You add them together. We can find the cell potential without thinking about what's oxidized, what's reduced, what's the cathode, what's the anode. When we subtract, was it cat minus an or an minus cat? Who remembers? I don't know. Okay? So this is practical. Any questions? An electrode has a negative electrode potential. Which statement is correct regarding the potential energy of an electron at this electrode? So what we want to think about here, the electrode has a negative potential. Electrons are negative. Do they want to stick around at this negative electrode? No, they don't. So an electron at this electrode has a lower potential energy than the standard hydrogen electrode, higher potential energy, or the same. Now, obviously, it's not going to be the same, right? So it's going to have a higher potential energy because it wants to get away. It's not happy with where it is. It wants to move away. So this has a higher potential energy. Any questions? So predicting the direction, spontaneous direction of redox reactions. We're going to compare the standard potential for each of the half reactions. The more negative one tends to lose electrons. The electrons are like, oh, this thing's negative, I want to get away. The more positive one tends to gain electrons. The positive's attracting the electrons, it's going to gain the electrons. So for a spontaneous reaction, the cell potential is going to be positive. So one way we can think about this is any reduction half reaction is going to be spontaneous when paired with the reverse of a half reaction below. And just some little notes here. Negative charge repels electrons. Electrons move from the more negative to the more positive. Oxidation is loss of electrons. Oxidation occurs at the anode. So, predicting the direction for this one. We've got a nickel half reaction and a manganese half reaction. Here, they're both written as reductions because that's how they're written in the table. And we can look up the cell potentials for the reductions. Which one of these do the electrons want to get away from more? The more negative one. This is more negative. Electrons will want to leave, right? Does this equation represent electrons leaving? No, it doesn't. Turn that one around. That represents electrons leaving. When we do that, we change the sign. So putting these two guys together, is going to give us plus 0.95 volts. That's the spontaneous direction. Oops. So is this written in the spontaneous direction? Is this shown correctly? The anode is the oxidation, right? An ox. So this is the one that we flipped around. This is the oxidation. Reduction is at the cathode, right? That's the reduction. And so yes, the electrons are going to flow from the anode to the cathode because the cell potential is positive. Any questions? Without calculating. Yeah, question.
Is that the best way to determine that? I guess I just have a hard time knowing which one to flip.
Yeah, which one do you flip? Well, if you want to find the spontaneous direction, you're going to want to add these together in a way that gives you a positive number. So here I have two negative numbers. I want to flip the more negative one because then it'll add to a positive. You could also just flip one of them randomly, add them together. Is that positive? Great, you picked correctly. Is it negative? Oh, it's the opposite. Okay, great question. Without calculating the cell potential, notice that all the cell potentials are missing here. Predict whether the redox reaction is spontaneous, and then sketch it. So, what do we have going on here? We have zinc going to zinc ions, plus 2 electrons. And we have nickel, plus 2 electrons, going to nickel. We don't have the numbers. On a previous slide, it said that if we pair a reduction with an oxidation that's below it in the list, that will be spontaneous. So you can kind of think of this as a priority list, like the FA 765, who gets first choice. So whoever is on top gets to keep their cell potential, and the one on the bottom has to reverse and go the opposite direction. And that will be a spontaneous reaction. The guy on the top is winning in priority. He's not going to switch. So the guy under has to switch. So we find these in here. Zinc, where'd you go? There it is. There's zinc, right? And then where's nickel? Above it, they're here. So the zinc would have to flip in order for this to be spontaneous. Did the zinc flip? Yeah. So this is a spontaneous reaction. So the guy on top stays the same. The guy underneath has to turn backwards. And that's what's going to be natural and spontaneous. So is it spontaneous? Yes, it is. Sketch the electrochemical cell in which the spontaneous reaction would occur. You will have to do a little bit of sketching, and it doesn't need to be beautiful. An ox and a red cat. An ox, I really like that, thank you. And a red cat. This is the side with the anode. This is the side that the oxidation occurs on. Which of these is the oxidation? The zinc. The zinc had to flip backwards. So this is a zinc electrode, and this solution contains zinc ions. The cathode is where the reduction occurs. That's the one that didn't have to flip. That's the nickel. So this is a nickel electrode and nickel, not sodium, nickel ions in there. The electrons are going to go from left to right. And we've got our salt bridge in here, and the ions are going to move. So we're supposed to label the anode on the left. So this is the anode. And this is the cathode. You could also think left to right. Those go in alphabetical order. Anode's always on the left, just because. Any questions? The mistake I see students make the most when they're drawing cells like this is they leave the salt bridge out. So, if you've got some electrical device and it's not making a full circuit, it's not connecting, it's not going to run, no matter how good the batteries are, right? If there's a gap, because a couple of electrons will go over and they're like, no, this isn't negative, this isn't positive anymore, that's not negative anymore, we're not moving, we're just going to sit here. You have to have a way for the charge to make a complete circuit. And so that's what the salt bridge is. Is this one spontaneous under standard conditions? You gotta know. I believe someone's, was looking at this ahead, which is great. Here's, what is wrong with my brain? Here's zinc. And this time we've got calcium. So let's try doing this without writing it all, writing out these half reactions. So this is the first one. He should be able to go the way he is, and this one would have to switch and go backwards, right? So this would be zinc ion on the left and calcium on the left. Is that how this one is? No, it's opposite, right? The zinc switched and the calcium didn't. That's not normal. This guy's more important, more powerful. It's like you're gonna, carrying a couch, right, out to the car or something. It's nicer to walk forwards, right? Especially if you're wearing flip-flops. Did you know that flip-flops used to be called go-aheads? Because you can really only walk forward in them. If you got flip-flops on, you do not want to be trying to walk backwards with the furniture, right? That's the lesser position. the more important the stronger person gets to walk forwards, the less important person has to walk backwards. Like you're doing it with your kid, you make your kid walk backwards, right? So is this spontaneous? No. We're talking about oxidizing these things. Oxidation is loss of electrons, right? So the oxidation of I minus would give us this if we balance the half reaction. Elemental I, as an atom doesn't exist. It's always found as an element, as a diatomic molecule, and we know that from the periodic table. So that would be this being oxidized, and if we oxidize the bromide, we're going to see a similar thing. This is going to make Br2, so we need 2 of these, we'll get 2 electrons. So we want to make this one happen and not that one. So these guys are backwards of what's shown here, right? So to oxidize, to cause this to be spontaneous, the thing we're pairing it with has to be above it. Let's find these guys. There's this guy and this guy. If we choose something up here, it's going to oxidize both of them. If we choose something down here, it's not going to oxidize either of them. So to do the one and not the other, we need something in the middle. Chlorine, H2O2, CuCl2, HNO3. So we see Cl2 in there anywhere? No, we see ClO2. Cl2 is up here, so that's not going to work. Oops, well, I guess that works. H2O2. H2O2 is over here. And that's the only place we see it. So that's also backwards, right? So that's not going to work. CuCl2. Well, you're not going to find that on there. You're going to have the copper or the chlorine. Where's the copper? Below. So copper's not going to do anything. HNO3. Well, we could look for the H+. We could also look for the NO3. Here we've got NO3 minus and the H+ together. So this is forward direction. That's going to oxidize this guy and not that guy. I personally don't like problems like that where you don't have the electrode potentials, because I would rather just add up all the electrode potentials and find out which one's positive, right? I don't like this. But if you can think about it as the guy on top gets to go forward with the furniture and the guy who's less important has to go backwards. And that's what's going to happen. If it's reversed, it's not going to happen. Any questions? Predicting whether a metal will dissolve in acid. Very similar. Acids, most of them, will dissolve metals by reducing hydrogen ions from the acid into hydrogen gas. And you've probably seen a reaction like this. You put zinc metal into like hydrochloric acid and you see it bubble, and you wait long enough and it goes away, right? All the zinc's gone because it became zinc ions. So this is the reaction that would need to be spontaneous for the zinc to dissolve, right? So this one is a reduction, and this is the oxidation. This one's backwards. So if this one, which is backwards, is below H plus, this will happen. If it's above, it won't happen. So metals whose reduction half reactions are below that of H plus will dissolve in acids. There's one exception that we need to understand, and that's nitric acid. Nitric acid can oxidize metals like copper that other acids can't, and that's because the nitrate is also participating. So copper can be dissolved in nitric acid, it can't be dissolved in hydrochloric acid. Yeah, gold can be dissolved in it too, but like HCl won't dissolve gold. So which metal dissolves in nitric acid but not hydrochloric acid? So we want to see, here's the nitric acid. Is it not on there? It's not. Let's see. Yeah, I should fix this. It's not on that one because it's on the second half of the table. So that's the HCl would do that. So then we need to find these Fe, Au, so here's gold and silver and iron. Yeah, so the Fe is right under this. I really need to fix this. So Fe3 plus, because you can't really tell. So that's under here. Yeah. So I really need to fix this table and include a couple more things because H plus is next and then the Fe is after that. So here's gold and here's silver. And down here's the iron. So dissolves in HNO3, but not in HCl. This is the HNO3. That means it's going to be below the HNO3, but not below the HCl. Yeah, so it's going to be the silver. And actually, this tells us that gold will not dissolve in nitric acid. So the silver will dissolve in nitric acid. Iron will dissolve in both of them. Gold will dissolve in neither. Any questions? Any questions? Are we at the end yet? Yes, we are. Yay! That's for next time.